In this fifth astrophysics video, we will discuss the stages from the initial collapse of a molecular cloud to the pre-main sequence, which marks the birth of a star. As always, our explanations will be clear and concise. We kindly request you to click the like button, subscribe to our channel, and activate the notification bell. Your support is crucial to the growth of our channel and helps us continue creating quality content. Thank you in advance for your support. A galaxy is not just a collection of billions of stars, but also a vast amount of gas and dust. These areas of gas and dust between stars are known as the interstellar median. The dust is composed of tiny grains that make up approximately 1% of the total mass of the interstellar median, primarily consisting of silicate and graphite grains that are coated with water ice. The dust is believed to be created in the cool outer layers of red giant stars, and then dispersed in the red giant winds and planetary nebulae. The gas consists of about 90% hydrogen, 10% helium, and trace amounts of heavy elements. The interstellar median is not uniform and contains several gas phases. The most important phases are listed in the table. Stars are born when gas and dust in the interstellar median comes together thanks to the gravitational attraction between the particles from which it is made. But now a question arises. In which component of the interstellar median can star formation take place? It's all about energy. If the region is not very dense, then the gravitational potential energy won't be enough to overcome the kinetic energy. The particles will not be bound together and the star is not likely to form. If the region is very hot, even if it is somewhat dense, particles will be transported very quickly, and again, the gravitational potential energy will not overcome the kinetic energy, and a star is not likely to be formed. Therefore, a star is likely to form if the region is cool and dense, which allows for gravitation to pull two particles together. Taking a look at the table, we see that these regions are the molecular clouds, also known as nebulae. Observations indicate that the giant molecular clouds are the likely sites where star formation can take place. Typical parameters are temperatures of 15 Kelvin, 10 to 5th to 10 to 6th solar masses, and 15 to 60 parsecs across. Low temperatures and high densities favor the formation of molecules. Therefore, most of the hydrogen in giant molecular clouds is in the form of hydrogen 2 rather than hydrogen 1. However, giant molecular clouds are very unlike stars. Thus, the question is, how do stars form from such molecular clouds? And the answer is that the stars form due to gravity. A cloud of gas contracts due to self-gravity. This contraction increases density and temperature of the core, initiating generation of nuclear energy. But now other questions arise. The mass of a star is much smaller than the mass of a giant molecular cloud. How can we reconcile this? And why do some nebulae remain nebulae, but some of them form stars? This problem was addressed by English astronomer Sir James Dean in 1902 while working at Trinity College, Cambridge. Dean proposed a criterion for the mass of a cloud of interstellar gas to collapse and form stars. The Jeans criterion simply states that for a star to form from a nebula, the gravitational potential energy of the mass of a gas must be greater than the kinetic energy of its molecules. The Jeans criterion specifies the minimum mass required for a cloud to collapse. A star cannot be formed unless the mass of the molecular cloud is greater than a certain critical value, called the Jeans mass, given by, where n is the molecular density. The collapse of a molecular cloud to form a star can only begin if its mass is greater than Jeans mass. Let us consider the Jeans mass of some interstellar structures shown in the table above. First, think about a region of atomic gas. These typically have number densities of 10 molecules per centimeter cubed, temperatures of 100 Kelvin, and mass of 1 to 100 solar masses. Plugging in these numbers, we get a Jeans mass approximated. Since the mass of these regions are less than its Jeans mass, they are stable against self-gravity and can be held up by pressure. On the other hand, let's try this for the interior of molecular clouds. These typically have number densities of 10 to 4 per centimeter molecules per centimeter cubed, temperatures of 12 Kelvin, and mass of 10 to 1000 solar masses. Plugging in these numbers, we get a Jeans mass approximated. Since the mass of interior of molecular clouds are greater than its Jeans mass, they are unstable against self-gravity and cannot be held up by pressure. The dense cores of giant molecular clouds are indeed unstable to gravitational collapse, consistent with being the sites of star formation. Giant molecular clouds are held together by gravity but are prevented from collapsing by the pressure of molecules moving in random motion. If a giant molecular cloud is originally in equilibrium with the surrounding interstellar medium, there must be some mechanism that perturbs the node giant molecular cloud so that some regions become denser than others. The gravity overcomes the thermal pressure and the cloud begins to collapse. The three major triggering mechanisms are as follows. Clouds passing the density wave areas where there is higher density of a spiral arm in a spiral galaxy. When molecular clouds pass through the density wave of a spiral arm in a spiral galaxy, they are compressed and collapse begins. Compression of clouds by a shock wave generated by a nearby supernova explosion. As the waves crash into the surrounding molecular cloud, gas tends to pile up and become compressed. Once shock waves have begun the compression of a molecular cloud, gravitational instabilities take over, dividing it into the fragments, denser than original molecular cloud, that eventually form stars. Cloud-cloud collisions in colliding or merging galaxies. This explains the starburst observed in merging galaxies. When two galaxies merge, giant molecular clouds collide with other molecular clouds. These collisions then induce condensations that eventually form stars. Once the gas cloud begins to collapse, gravitational potential energy is released, If this energy were converted directly to thermal energy, the temperature would rise, and according to Jean's equation, the Jean's mass would increase. At some point, the Jean's mass would reach the cloud mass, halting the collapse, and we would not exist. However, in the early stage of collapse, the cloud is transparent to infrared radiation and can cool efficiently by converting kinetic energy of its molecules and atoms into infrared photons, which can escape the cloud. Since the energy of collapse is immediately radiated away, the cloud won't heat up. We call this an isothermal collapse, and the cloud is essentially in freefall collapse. The freefall timescale is the time required for a cloud in freefall to collapse from R equals R sub 0 to R equals 0. This final condition is never reached and is given by for typical molecular cloud, the freefall scale is which is about 1,000,000 years. This is how long it would take a molecular cloud to collapse if it were affected only by gravity. This time is very short by astronomical standards. As the cloud collapse density increases, the increasing density of isothermal clouds implies that the Jean's mass decreases so that small pieces of the cloud start to collapse on their own. An increase in density also means a decline in freefall time, so these small dense clumps collapse faster than the overall cloud. Instead of one giant cloud undergoing a monolithic collapse, the cloud fragments into small collapsing pieces. This process is called the fragmentation process. So what stops this fragmentation? The increasing density of the collapsing cloud fragment renders the gas opaque even to infrared photons. As a result, radiation is trapped within the central part of the collapsing cloud. The collapse turns from isothermal to adiabatic. This results in an increase in temperature and a subsequent increase in the Jean's mass. When the Jean's mass equals the real mass of the fragments, the fragmentation process stops. From here, the cloud absorbs all the gravitational energy from the collapse. It heats up and starts to act like a black body. Higher temperature means higher pressures. At this point, the fragments reach hydrostatic equilibrium. At what mass does this happen? More recent evaluations show that the minimum Jean mass for a fragment is half the solar mass. This is the order of magnitude for the mass of the fragments of clouds which become stars. In other words, collapse halts when the fragment masses reach star-like masses, and at this stage, we start to speak of a protostar. Now let's see what the initial shape of these clusters looks like. Due to the gravitational collapse, the clusters contract and begin to rotate. In the center of each of them, a high-density region develops that is surrounded by a low-density envelope. In other words, the cloud flattens and there is a protostellar disk rotating around the protostar. Matter continues to flow inward from the outer parts of the clusters. The protostar begins to take shape deep within the surrounding cloud of cold dust gas. Before we proceed, it's worth highlighting a few points, a few properties of the stars. We just saw that stars form inside a molecular cloud, therefore, stars tend to form in groups because of where star formation occurs. Stars are often found in clusters. The chemical composition of stars is quite constant because they share the chemical composition of the same molecular cloud. The masses of stars vary from 1/10 of the solar mass to about 50 solar masses. This is probably due to the minimal mass of genes that stops fragmentation. Stars are often found in pairs. Unlike the Sun, the vast majority of stars have a binary partner. Astronomers estimate that up to 85% of all stars may exist in systems with 2 or 3 stars. Some astronomers think that stars are actually born as multiples. Others think that protostars are attracted to each other by gravity, forming pairs or multiple systems. Now that we understand something about how the star formation process begins, let us turn our attention to the objects that are created by it, that is, protostars. The surrounding gas continues to free fall onto the protostar core, so that the next phase is dominated by accretion. When the gas hits the stellar surface, it comes to a stop and its kinetic energy drops to zero. This energy must then go into other forms. Some of it goes into internal energy. The core heats up and part of which is radiated away, providing the luminosity of the protostar. This leads to an increase in central temperature, and the growing gas pressure acts to stabilize the core. When the temperature of the core reaches 2000 Kelvin, the average particle energy is comparable to the dissociation energy of molecular hydrogen. Hence, during this phase, most of the gravitational contraction energy can be absorbed through the dissociation of a small fraction of the total molecular hydrogen. As a result, the core becomes dynamically unstable and a collapse occurs, during which the gravitational energy released is absorbed by the dissociation molecules without a significant rise in temperature. When molecular hydrogen is completely dissociated into atomic hydrogen, hydrostatic equilibrium is restored and the temperature rises again. Somewhat later, when the temperature of the core reaches 10 to the power Kelvin, then helium are ionized and the protostar collapses again. After all dissociations and ionizations are completed, the hydrostatic equilibrium is restored. We can estimate the radius and temperature of a protostar after all these processes. A few important things of note. The temperature is independent of the mass of the protostar. The core is still too cool to ignite nuclear reactions. The mean density of a protostar of 1 solar mass and 100 solar radius is 10 to minus 6 grams per centimeters cubed. At such low temperature and density, the energy transport by radiation would be very inefficient. So the star is almost completely convective, and the macroscopic movement of the material carries energy. The protostar is chemically homogeneous. Convection increases the surface temperature to 10 to 3 Kelvin and thus also increases the luminosity. At this stage, the protostar is in a physical state that can be described by the equations of stellar evolution, so we will call it a star from now on. Stars in this phase are totally convective. The radius is large and the luminosity is high. and from now on we will understand the movement of the star in the HR diagram until it reaches the main sequence. Let's start by placing three stars in the HR diagram whose final masses on the main sequence will be 50, 1 and 500th solar masses respectively. When a protostar becomes fully convective, the increase of temperature at the protostar surface will stop, so fully convective stars occupy the same vertical band at low temperatures from 3000 to 4000 Kelvin. Because protostars have almost the same effective temperature, their luminosity is defined by their radius because luminosity is proportional to radius squared. Since it is still too cool for nuclear burning, the energy source for its luminosity is gravitational contraction. As the stars are contracting, so their luminosity decreases. They then evolve along a specific descending line in the HR diagram. Look at the HR diagram now. This line is called the Hayashi line or Hayashi track. During the descent along the Hayashi track, the star is contracting and the temperature and density in the star rises. A radioactive core will form at the center and grow in mass as the star evolves. When it reaches a mean temperature of 10 to 6 Kelvin, the energy can be transported by radiation. Because the protostar is no longer convective, the downward evolution along the Hayashi track stops. This corresponds to the point of minimum luminosity on the Hayashi track. When the radiative core appears, the energy to escape more readily into the convective envelope, causing the luminosity of the star to increase. The effective temperature continues to increase since the star is still shrinking. The star is no longer fully convective and it has to depart from its Hayashi track. The star executes a sharp leftward turn on the HR diagram. Look at the HR diagram now. This line is known as a Heine track. When temperatures reach the order of 10 to 6 Kelvin, some nuclear reactions have already set inside the star, although they are not relevant from the point of view of energy production. When temperatures reach the order of 10 to 6 Kelvin, deuterium is transformed into helium by proton captures, which destroys all deuterium present in a star. Sometime later, at a core temperature of about 2.5 times 10 to 6 Kelvin, lithium is destroyed by the reaction chain. When deuterium burning ceases in the core, the star reaches a new equilibrium. The star in radiative equilibrium has not yet started nuclear fusion, so it will keep slowly contracting to cover the loss of energy by radiation. Its mass and luminosity remains constant while the surface temperature increases slightly. This means that its evolution track will now be approximately horizontal as the star moves toward the main sequence. When the central temperature reaches 10 to 7 Kelvin, hydrogen burning is ignited in the stellar core. Once nuclear fusion begins, the protostar has a strong energy source which can heat up the gas and provide a large pressure to balance gravity. Hydrostatic equilibrium halts the collapse and the star is born, and the so-called main sequence phase starts. Very low mass stars and very high mass stars evolve a little differently. Very low mass stars never develop a radioactive core and they are fully convective, and thus reach a position close to the main sequence immediately after the Hayashi track, moving almost vertically along the HR diagram. Very high mass stars are fully radioactive in the beginning on the Hayashi track and begin moving nearly horizontally across the HR diagram on the Heinei track. Even heavier stars are born onto the main sequence.